Welcome back to Organic Chemistry. Continuing on with our discussion of alkenes, in this section we're going to look at the various ways to synthesize alkenes in the laboratory. Okay, let's go on. Alright, so let's move on to talk about making alkenes. There are three essential ways to make alkenes. And we're going to find as we go through this semester that we're going to see a lot of times things that are either review or things that reinforce each other, because we're going to be looking back to things that we've already done to make these types of functional groups, but we'll see that they can be used to make something else, but then of course when we talk about that something else we'll be reviewing some of the chemistry again. And one way that we already know from last semester to make alkenes is that we can make alkenes via elimination reactions, and we'll go through those briefly in a moment. We'll also see two new ways of making alkenes, something called a Wittig reaction, which is kind of different from some things you've seen, but we'll also relate it to things that you've seen before as well. And something that is pretty new, reduction of alkynes, and we'll talk about that. All right. So first, let's just remind ourselves, I'm not going to belabor these because we spent a lot of time on this in the first semester of organic chemistry. You can make alkenes via elimination reactions. You know that if you've got a good leaving group, and things like halides or resonance stabilized leaving groups make good leaving groups, and you've got a base, you can pull off, using that base, you can pull off a hydrogen from the next position over from the leaving group, form a double bond, and have the leaving group get kicked out. And if this all happens in one step, we call that an E2 mechanism. But if first the leaving group left and then the hydrogen was pulled off to make a pi bond, that was an E1 mechanism. And last semester when we looked at these, we spent some time on it, and we learned, for instance, what makes a good leaving group. As I just mentioned, halides pretty much make good leaving groups, but also resonance stabilized things like tosylates and acetates can make great leaving groups. Stronger bases will tend to favor the E2 elimination because in that case the base is part of the rate limiting step. But weaker bases won't do E2 elimination, but they can take part in the second step, which is not rate limiting, for an E1 elimination. We also found last semester that the solvent was very crucial to the E1 mechanism because you form these cationic intermediates, and that's most likely to happen in a polar medium, but they won't happen in a nonpolar solvent. The E2 elimination, on the other hand, could happen in either a nonpolar or a polar solvent. And finally, both of these reactions tend to happen more often when the leaving group is at a more substituted position, such as a tertiary position. In the case of E1, that's necessary because if you have a leaving group at a tertiary position, when it leaves, you form a tertiary carbocation, which we know, such as this, which, as we know, is more stable than a secondary, and it's much, much, much more stable than a primary carbocation. In the case of the E2 elimination, when we've got a strong base, if we had our leaving group at a primary position, a sterically unhindered position, we'd be more likely to do an SN2 reaction instead of an E2 elimination. But if we're at a tertiary position, we can't do an SN2, so we'll have to do an E2 for steric reasons. A secondary leaving group at a secondary position, it's going to be sometimes more SN2 and sometimes more E2, and it kind of depends on the particular Lewis base that's involved. We also saw last semester, and you've already done this reaction in lab, that you can get dehydration reactions under acid-catalyzed conditions. And remember the mechanism of this. H2SO4 is a strong acid. Let's use the Bronsted-Lowry definition. It's a source of H+. Oxygen's got lone pairs, and if one of those oxygen pairs reaches out to an H+, we're going to make oxygen with 3 bonds, one lone pair, formal charge of +1. if we were to break this bond, we'd get a carbocation. And under these conditions, sulfuric acid and heat, you know that carbocation intermediates could be part of SN1 or E1, but these conditions favor E1. And so what's going to happen is you're going to pull off a hydrogen for the next position over to make a double bond. Now, this is an E1 mechanism, as I've just described it. In lab, you've learned that this can be actually a little bit more complex, and there can be a competition between E1 and E2, but we're not going to worry about that right now. Now, on that previous slide, you may have noticed that I said you remove a hydrogen from the next position over, but there's two possible next position overs that have hydrogens. So we're going to have to worry about selectivity. When we talk about eliminations, we'll find that there's a question of what's called regioselectivity. That is, can we select the red hydrogens or the blue hydrogens if our leaving group is here? So we're going to pull off a hydrogen from the next position over, but that could be here or here. And the factors that favor one over the other, that's called regioselectivity. It's selective. Chooses one over the other based on the region. And what is that if you were to remove the blue hydrogen, you would form one product. And if you were to remove one of the three red hydrogens, you'd form the other product. But if you go into lab and test, you'll find the blue product is preferred. Now why? Well, we already talked about the relative stability of different alkenes. And we mentioned at that point that the more carbon groups around the sp2 hybridized carbons, the more stable the alkene. Here's my sp2 hybridized carbons. There's one carbon group attached to an sp2 hybridized carbon. The other three are all hydrogen. Here, there's three carbon groups around the sp2 hybridized carbons. Only one hydrogen, and therefore this is preferred. In addition to regioselectivity, in the case of the E2 elimination, you also get stereoselectivity. Now I should notice that the E1 mechanism, since the two different bond breaking steps happen separately, you can get a mixture of stereoisomers, just like in the SN1 you get a mixture of stereoisomers. But in the E2 elimination, so if I have, in this case, my leaving group, if I had a strong base, we know we're going to pull off this hydrogen that I'm highlighting here for Seitzef's reasons. By the way, I guess I didn't say this, but this recognition that you form the more substituted, that is the alkene with more carbon substituents, alkene is favored. That's called Seitzef's rule. Okay, Seitzef tells us that we're going to remove this hydrogen and make a double bond between these two positions. Again, there turn out to be two possibilities. Because if I have a 6-carbon chain with methyls at 2 and 3 and a pi bond between 2 and 3, well, there's two stereoisomers that fit that description. This is the E and this is the Z. You go and you find out that there's some selectivity, and it comes down to this. To get the bond to form, the pi bond to form, we have to have the carbon-hydrogen bond and the carbon-bromine bond line up with each other. There's two ways that they can line up. Here I'm showing a Newman projection looking down the, I guess it's the 3 to 4. Did I say 2 and 3? I meant 3 and 4. Looking down the 4 to 3 bond, sorry. And I'm going to look at a Newman projection. I'm going to see either something like this or something like this if I want to consider those conformations that allow the CH and carbon-bromine bond to line up. But when we look at these two Newman projections, we know that this one is preferred because it's staggered as opposed to this one that's all eclipsed. And that one, if I make my double bond here, notice if I make the pi bond here, notice two methyls are kind of pointing the same direction, and two carbon groups are pointing the same direction. That's like if I put my eyeball here, look down this, two carbon groups on my left, and two 1-carbon groups on my right. That would be the perspective if I was looking down this, which is the same perspective as we're looking down the Newton projection at the starting material. But the starting material has to get into the reactive conformation, which is either going to be this one or this one. But the starting material is much more likely to get into this reactive conformation. And then that is going to smoothly lead to the transition state, which will smoothly lead to the product, in this case, for the Zusammen isomer. All right, hopefully those were pretty much review. The idea of E1 and E2 elimination, and even the idea of using acid-catalyzed dehydration, where our leaving group was a water molecule, rather than an alkyl halide or something like that. But there are other reactions that we have not yet learned. For instance, the Wittig reaction. Let me just show you the Wittig reaction first, and then we'll go through it in detail. If I bring together a ketone or aldehyde, something with a CO double bond, such as this, and this weird thing is called a phosphorus ylide. And notice it's got a carbanion right next door to a phosphorus plus. And so even though carbanions are pretty unstable things, and they're not something you can really leave sitting around, you can form this sort of thing. And the reason you can form this particular carbanion is because the negative charge is right adjacent to a phosphorus plus. And so forming that is at least doable in a lab setting. But this is a carbanion, and carbanions do a relatively small number of things, one of which is add to carbonyls. Let's look at the pieces of our product. And we see our product, alkene, involves kind of a 3-carbon part and a 2-carbon part on either end of the carbon-carbon double bond. Well, our starting materials had a 3-carbon part and a 2-carbon part, and it makes sense that somehow this phosphorus ylide, the carbon, and gets connected to this carbon, and somehow we make a double bond. But this phosphorus group and this oxygen group aren't there in the product, so they go away. How do they go away? It turns out in a balanced equation, they go away as this phosphorus oxide species. Okay, before we can go any further, let's talk a little bit about this phosphorus ylide. That's this odd-looking species here. This is a zwitterion. A zwitterion is a molecule that is net neutral but has positively and negatively charged regions, and not just partial positive and partial negative, but a full plus and a full minus formally. And we see that here, a plus on phosphorus and a minus on carbon. When those are on adjacent positions, that's called an ylide. So this is the structure I prefer to draw for the phosphorus ylide. You will see some people draw this as a carbon-phosphorus double bond. Notice we're going hypervalent on phosphorus here. That is, we have more than 8 electrons shown around phosphorus, which is okay because we've got d orbitals, and so you can draw it that way. We're not really violating the octet rule doing so. For instance, you've seen H2SO4 having more than 8 electrons around sulfur. Sulfur is next to phosphorus. But I'd prefer to draw it like this because I think this resonance form better shows the overall properties of the phosphorus ylide. Where do we get this thing from in the first place? We get it from some primary alkyl halide. If I had a primary alkyl halide and triphenylphosphine, triphenylphosphine is a readily available compound. It's got this lone pair that it's actually a pretty good nucleophile. I know when we first introduced SN2, we talk about strong nucleophile versus weak nucleophile, and if something is neutral, we generally call it a weak nucleophile. Well, it's really, strong versus weak. It's really a continuum from the strongest to the weakest. And as neutral things go, this is a pretty good this is pretty strong nucleophile because this lone pair on phosphorus is pretty willing to react. Has to do with being in the third energy level as opposed to the second. But if this reaches out and does an SN2, adds to here, kicks out the bromide, well, we initially form a carbon-phosphorus bond, which has a formal charge of +1 on phosphorus. And if we treat this species, this positively charged phosphinium, with a strong base, LDA, butyl lithium, some other strong base. We can pull off one of these two hydrogens from the adjacent position to make this ylide. Normally you don't deprotonate sp3 hybridized positions, but here our anion is stabilized by being adjacent to this positively charged phosphorus. So this is the phosphorus ylide. Okay, let's go back to our reaction. When we take that phosphorus ylide, here I've got just a methyl group as my R on the previous slide, and I react that with some ketone or aldehyde, a reaction will occur to make a double bond between, say, the carbon part of the ketone or aldehyde and the carbon part of my phosphorus ylide. And then the byproduct is this triphenylphosphine oxide, where the phosphorus and the oxygen get together, and they float away as byproduct. Actually, it'll precipitate out, to be a little more precise. Okay, how does this work? Well, this phosphorus ylide, it's got a carbanion. And carbanions are really strong nucleophiles. And if I don't know anything else about a carbon-oxygen double bond, I know that they've got this resonance structure that leads to a partial positive charge on carbon. And therefore, if we look at the mechanism, it's reasonable to imagine a carbanion reaching out to this position, pushing electrons onto oxygen. Notice that's exactly like the Grignard reactions that you learned about last semester, where a carbon minus added to this position kicked electrons up to make an O minus. But unlike in the Grignard reaction, where this stuck around until you protonated and then you got an OH, this oxygen is right next door to a positively charged phosphorus. And there's going to be an attractive interaction between those things. This negatively charged species is going to reach out to interact with this positively charged center to make an oxygen-phosphorus bond. But this species is strained. It's a four-membered ring. We know that four-membered rings aren't the best of things, especially once we put in this phosphorus, because carbon-phosphorus and oxygen-phosphorus bonds are longer than, say, carbon-carbon bonds. So this ring is more strained than just even a plain old four-membered ring. And so it wants to fall apart. So we can form it, but it's going to fall apart. If I break this bond, I'd go back this way. But it turns out the phosphorus-oxygen bond is really strong. Just accept that for now. And so it's harder to break that than to break these others. So let's break this bond. If I broke this carbon-oxygen bond, well, that would put a plus charge here, and that's probably not the most stable thing. So instead, let's break two bonds simultaneously. Let's break this carbon-oxygen bond to make an O minus. But simultaneously, let's have this carbon-phosphorus bond break, and those two electrons get shared with that carbon to make a carbon-carbon pi bond. Notice my byproduct is this triphenylphosphine oxide, which will, as I mentioned before, precipitate out of solution, and that will help push this forward. I don't want to belabor this, but the simple Wittig reaction gives a mixture of stereoisomers. If on the previous example I used a symmetrical ketone, here I've got an aldehyde, propanal. And notice, depending on the orientation of this group to this group, I will get two different possible stereoisomers of my alkene. You get a mixture, more Z than E, it turns out. There are variations on the Wittig that help you control the stereochemistry more specifically. This, for instance, is the Horner-Wadsworth-Emmons reaction. And notice that this thing is very similar to the triphenylphosphine oxide. And it tends to give a more selective product. I don't want to get into this, but just all I really wanted to point out is that there are stereochemical issues with the Wittig, and there are more things on heaven and earth, Horatio, than dreamt of in your philosophy, right? There's more reactions than we're going to cover in just this section, but there's reactions that are sort of very similar to the reaction I showed on the previous slide. Okay. This Wittig reaction can be a very useful way to make alkenes. For instance, let's say I want to make this compound. And if I wanted to think about the different ways I could make this compound, of course it has an alkene, and we've learned that we can make alkenes by elimination reactions. So we could imagine a reaction in which I had an OH and I did an elimination and I made an alkene. But let's say we wanted to make this by a Wittig reaction. If I make this via a Wittig reaction, note there are two parts. There's the part I've highlighted in blue and the part that I've highlighted in red. And those are going to come together in the Wittig reaction to make a carbon-carbon double bond. It could be that the part I've highlighted in blue comes from the phosphorus half of the ylide reaction, and the part I've highlighted in red comes from the carbonyl part of the Wittig reaction. Or it could be that the blue part comes from the carbonyl part and the red part comes from the phosphorus ylide part. Either one's fine, because in the product, you just end up with a double bond between these two positions, and the phosphorus and the oxygen have gone away as triphenylphosphamine oxide. So notice this same alkene could be formed in two different Wittig reactions. If we were planning on performing this synthesis, we might make a choice one way or the other based on, for instance, the availability of the various starting materials. It might be that you go to the shelf and we've got a lot of bromobenzene, and that's the precursor to the triphenylphosphine ylide. Remember, we did an SN2 and then a deprotonation to make this ylide, and so we choose to make this. Or let's say we go to the shelf and we got a bunch of benzaldehyde, that's this guy, and so we choose to do this way. Either one would give us the same product. Okay, there is a third way of making alkenes by starting from alkynes and going from a triple bond to a double bond. I am not going to go into that at this time. We'll talk about this when we go through alkyne chemistry. All right. I'll let you go through and predict the products, but we can go starting from the starting materials on the left. We could do an elimination reaction. In the first two examples, the first one is an E2 elimination, and the second is an E1 acid catalyzed dehydration, or a Wittig reaction in the third example, and they give the products shown.